students can understand and relate to. So, like it was shown in the timetable for today's class, we're going to be dealing with the atomic structure and periodic classification. I'm sure you're all excited about what we're going to be doing in today's class. Is that correct?
Yes.
Very well then. So without wasting any time, let's get into what we have for today's class. And I want to please crave our indulgence. If at any point you have a question, if there's something that is not clear to you, please feel absolutely free to stop me. Okay? I would be more than happy to clear any confusion that you may have in the course of today's class. So that being said, let's go into what we have for today. Three, two, one, and let the class begin. Today we're going to be dealing with atomic structure and periodic classification. Just to clarify, I want to know if you all can see what is on the screen right now. Can you see it?
Yes.
All right, beautiful. So this is what we're going to be dealing with today, atomic structure and periodic classification. So we have some learning objectives that you should be able to carry out by the end of today's class, okay? By the end of today's class, there are some aims I want you to be able to achieve. Aim number one is that I want you to be able to recall the basic structure of the atom. Okay, there are certain things that make up the atom. There are protons, neutrons, and electrons. We're going to be seeing each and every one of them. I want you to be able to recall their basic structures. And then at the end of today's class, I want you to be able to define key terms. Okay, and I also want you to be able to explain electronic configuration. And then finally, you'd be able to identify groups and to identify periods on the periodic table. So let's get into what we have for today's class. One more thing, if by any chance maybe the network is fluctuating from your end and you're not able to um get everything we're doing in today's class, don't worry. This class is being recorded. It will be uploaded to my YouTube channel. And once it's done, I'll send in the link for you to be able to catch up. If I'm audible enough, please let me see your reaction on the screen so that I'll know that you're following. Can you hear me perfectly well?
Yes.
All right. Beautiful, beautiful. So let's begin. By way of introduction, I want you to imagine something. So we are SS2 students. I presume we're all SS2 students, okay? So we have a bit of background knowledge about science and chemistry. So I want you to imagine this. One of the elements on the periodic table is sodium. And one of the characteristics of sodium is that it is a soft, silvery metal. And its character is that it reacts so violently with water that it can cause sparks. There is a video that I'm going to be showing us in a few moments. Okay? In as much as sodium is very, very reactive, there is something that is very close to sodium on the periodic table, and that element is called neon. Neon is only a few spaces away on the periodic table from sodium, but neon is absolutely unreactive. Now, one question somebody might want to ask at this point is, why is it that sodium is very reactive and neon is absolutely unreactive, even though they are close to each other on the periodic table? The answer is on the next page. One element is dangerously reactive, while the other one is completely stable. The answer lies in what we're going to be studying today, atomic structure. Are you all following me?
Yes, sir.
Very good.
Yes.
Atomic structure.
Yeah.
An atomic structure is simply the way protons, neutrons, and electrons are arranged inside atoms. I said I was going to play a video for us, so I want us to just sit back and watch the video that I'd be playing for us very quickly. Just hold on. There's a video I want to play for you to show you how reactive sodium is. All right, can we all see the video that is playing on the screen right now?
Sodium metal.
Yes, sir.
Okay. Can you hear what the person is saying?
No.
No.
Cut it with a key.
Can you hear what the person is saying now?
Yes, sir.
No.
Let me play the video. The person is doing an experiment where sodium is going to be thrown inside water. You will see what will happen. Just watch.
Sodium metal, very soft. So you should be able to just cut it with a key. Something that soft, you wouldn't think would be dangerous. But check this out. Go. Sit down.
Did you all see what happened?
Yes, sir.
Very good. Now, sodium that was being thrown into water, and you saw how that thing exploded. Now, on the periodic table, sodium is not far from neon. One is very, very reactive and violent when it is thrown inside water, but the other one is non-reactive. And we are saying that one reason why this happens is the atomic structure. So the atomic structure is simply the way protons, neutrons, and electrons are arranged inside an atom. So these tiny arrangements control how an element behave. Thus far, is anybody confused about anything? Is there any confusion? Is there anything that anybody doesn't understand thus far? Can we proceed?
No, sir.
All right.
No. Yes, sir.
All right, so let's talk about atomic structure. So I always like my classes to be very interactive. I want to be someone who learns from my students as much as they learn from me. So I want you to pay attention to what is on the screen right now. In your own words, if I say atomic structure, what comes to your mind? What do you understand by that phrase, atomic structure? I want one or two people to um, give their opinions and then we'll proceed. Atomic structure. What comes to your mind?
The structure of an atom.
Okay, very good and straightforward. Atomic structure simply deals with the structure of an atom. I like that, simple and straightforward. Yes, anybody else?
Things that makes up an atom.
Okay, very good. The things that make up an atom. Everyone who contributed did so beautifully well. I want you to pay attention to the two words, atomic and structure. The word atomic was actually coined out from the word atom. And I'm very sure that everyone here knows what an atom is, right? The smallest part of a substance that retains the chemical property of that substance. And then the second word is structure. When we say structure, we are simply talking about how something is built up, the form that something takes up. Am I communicating this afternoon? Hello, am I communicating? Can you hear me? Am I audible enough?
Yes.
Beautiful. So let's define an atom starting first. An atom is the smallest part or the smallest particle of an element that can take part in a chemical reaction while retaining the properties of that element. Now, one element that is very abundant in our world today that we use and we have interactions with every day is the element called oxygen. oxygen is spelled as Oxygen. Now you can see I have an image of a person breathing in. And we all know that when you breathe in, the gas or the element that you take in is called oxygen. Now, oxygen is an element on the periodic table, and it is made up of tiny, tiny oxygen atoms that look like this. This is what the structure of an oxygen atom looks like. Can you see what is on the screen right now?
Yes.
Very good. So
Yes,
this is
sir.
just very good. I'm so excited that you're following through with today's lesson. So this is just an example of what the structure of an atom looks like. So we're going to be talking about all these bits and pieces. You see these line circles that are going round, all these balls that are surrounding the circles. We're going to be talking about what each and every one of them means. So I want you to follow me step by step as we go through this class. So at this point now, we're talking about the main parts of an atom. Before we proceed, I want someone to refresh our memory. What is an atom? Can you please quickly define an atom for us?
An atom is the smallest part of a substance.
Yes, the smallest part of a substance. Do you want to add anything to that definition?
An atom is the smallest particle or substance of an element that can undergo chemical reaction while,
Okay.
re- while retaining chemical properties.
Okay, beautiful, beautiful, beautiful. I like how you put it. The smallest particle of a substance or an element that can undergo a chemical reaction and still retain the properties of that element. I like how you put it. Absolutely beautiful. So now, there is something you must also know. As small as the atom is, there are also smaller particles that make them up. Just like, for instance, when you want to build up a house, you are going to use something that is called bricks. Am I correct on that? In the
Yes,
same
sir.
way, thank you. In the same way, an atom is made up of smaller particles that make it up. Those smaller particles are called subatomic particles. And we want to see what each and every one of them are. The first one we are looking at is the particle that is called the proton. Somebody say after me, proton.
Proton.
Very good. Now, the proton,
Proton.
yeah, thank you. The proton is the subatomic particle in an atom that is positively charged. Now, don't get confused. This diagram that I just labeled over here right now is the diagram of what an atom or an atomic structure looks like. You can see some balls, some green balls that are scattered all across the atom. Those are not the protons. We're going to be seeing what they mean. But for now, the first subatomic particle that we want to know is the proton. You see these yellow balls that have plus signs on them. They are the ones that are called the protons. So, if we want to define the proton, we'll simply say the proton is a subatomic particle that is positively charged. I'll take that one more time. The proton is a subatomic particle that is positively charged. You can see it over here. The charge that a proton carries is positive, and its location is inside the nucleus. Are we all following, please?
Yes.
Very good. Now, where is the nucleus inside this atom? You see this part that is the center. I just circled it right now. That part that I just circled is called the nucleus, also known as the center of the atom. That is the place that contains the proton and the neutron. We're going to be seeing what the neutron also means as we progress. So the first subatomic particle is the proton. The second one is called the neutron. Somebody say neutron.
Neutron.
Thank you very much. Neutron. The neutron is a word that was derived from the other word called neutral. Neutral was the word where neutron was derived from. What is the neutron? The neutron is a subatomic particle that has no charge or zero charge. No charge or zero charge. That is what the neutron is. And the location where the neutron is found is inside the nucleus. You can see this part here that I circled. That is the center of the atom. That part contains both the proton and the neutron. Are we all following? I believe we are. The next subatomic particle that we want to look at is the electron. All these things are important because they are serving as the foundation where we are going to build our knowledge of the atomic structure on. So the next particle we're looking at is the electron. The electron is a subatomic particle that is negatively charged. So we have looked at three thus far. We've looked at the positively charged subatomic particle. We've looked at the subatomic particle that has no charge. And then we are looking at the negatively charged subatomic particle. You can see these green balls over here that have minus sign written on them. They are the ones that are called electrons. And they are negatively charged. Where is their position? They are moving around in energy levels, also called or also known as shells in an atom. Thus far, so good. Is anybody confused about anything? Is there anything anybody would want me to clarify?
No, sir.
All right, so let me throw the question open to the class. What are the three main subatomic particles that you know? David, let me hear you speak. The three main subatomic particles that you know.
Proton, neutron, and electron.
Which of them has no charge?
Neutron,
Very good. Which of them has a positive charge?
proton.
All right. Mr. Francis, how many subatomic particles do we have? Mr. Francis, how many subatomic particles do we have? Nifemi, do you want to attempt that question? How many subatomic particles do we have?
3.
Very good. What are they?
Proton, neutron, and electron.
All right. Can you define for me what an atom is?
Yes, an
All right.
atom is made of less particle.
Okay, the smallest particle of a substance or an element that retains its chemical properties. Thank you very much. So now, thus far, we have seen a few things, and as we progress, we're going to be seeing more and more things. As far as the atom is concerned, there are some parameters or some characteristics about it that you need to know. Okay, and that is moving us to the next subtopic that we are looking at, the atomic number and the mass number. The atomic number and the mass number. Remember, I showed you.
You're on message. Okay, thank you.
Are we together?
Yes, sir.
All right then. So we're looking at the atomic number and the mass number. Earlier on, I showed you what the structure of an atom looks like. You can see another atom or another structure of an atom drawn over here. We saw the subatomic particles, which is why we're moving on to this next thing. The atomic number, which is what we want to define now, is the number of protons in an atom. The atomic number is the number of protons in an atom. It also equals the number of electrons in a neutral atom. For example, I have the drawing of the atomic structure of sodium. Sodium is one element on the periodic table. And if you look at this structure over here, you can see what the structure of sodium looks like. Sodium has 11 electrons in its atomic structure. Watch with me as I count. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then finally 11. So the number of electrons that are present in a neutral atom. By the way, a neutral atom is simply an atom that has not undergone any chemical reaction. So as far as an atom has not undergone a chemical reaction, we say it is neutral. So we can see this atom over here having 11 electrons. So the number of electrons that are present in an atom, that is what is called its atomic number. And in chemistry, we represent the atomic number using a symbol called Z, a capital letter Z. All right, so now that we've dealt with the first parameter we want to look at, let's move on to the next one. The next one that we're looking at is the mass number. We've seen what the atomic number is. Now we want to look at what the mass number is. The mass number is simply the total number of protons and neutrons that are present in the nucleus. For example, sodium, which is an element on the periodic table, has a mass number of 23. The number of protons that it has is 11, and the number of neutrons that it has is 12. So when you know the number of protons and the number of neutrons, when you add the both of them together, it gives you the mass number. If it is clear to you thus far, can I see your reaction on my screen right now? If you're following and you can hear me clearly, please, can I see your reaction on my screen? All right, very good. Thank you very much. I saw your reaction, Nifemi, and I believe the same goes for other people. Now, this is how it goes in chemistry. When we want to represent an element, we use the symbol X, just like this that I just did. The atomic number is denoted by the symbol Z, written at the left bottom corner, and the mass number is written by the symbol A at the top left corner. So for instance, if I write the symbol of sodium Na, if I want to show the atomic number Z, I will write it at the bottom left corner, 11 like this. And when I want to show the mass number 23, I will write it at the top left corner like this. So this is the symbol, this is the atomic number, and this is the mass number. I'm sure we're all following. So now that we have seen what the atomic number and the mass number is, that brings us to the next concept that we want to see, the concept of isotopes. Now, I want one or two people to please define for me in their own understanding, what do you understand by the word isotopes? Can you unmute yourself and please tell me, one or two people?
Isotope can be defined as an element with the same atomic number but different mass number.
Thank you very much. Very correct. Does anybody else have any other definition of what an isotope is?
Isotopes
are elements that have the same number of protons but different mass numbers.
Thank you very much. Remember, we said that the number of protons is what the atomic number is. So when elements have the same number of protons, that is atomic number, but their number of neutrons are different, we call them isotopes. Now watch this. Hydrogen, for instance, has 3 isotopes, and I have the structures written all out on the screen right now. The first one is called protium. The first isotope of hydrogen is called protium, P-R-O-T-I-U-M. Now, protium has just 1 proton. In other words, the atomic number, or letter Z, is equal to 1. and then it has 0 neutrons. So if I want to find the mass number for protium, I would simply add the number of protons, which is 1, plus the number of neutrons, which is 0. So for this guy over here, the mass number is 1. Now I want you to do for me, what will be the mass number of deuterium? Somebody please do for me and get me the answer very quickly. Deuterium. What would the answer be? The mass number for deuterium?
2.
Very good. Why is it 2? Because the atomic number or the number of protons is 1, and then the number of neutrons here is 1. So the total will now be 1 plus 1, which is 2. Thank you very much. How about for tritium? What would the mass number be?
3.
Thank you very much. Why is it 3? The mass number
Because
is... Yes? Yes, I'm
has
listening.
it has 2 neutrons and 1 proton, and the
Thank you.
mass number is the proton and the neutrons combined.
Thank you very much. That was what I was expecting to hear. It has 2 neutrons and 1 proton, and the mass number is the number of protons plus the number of neutrons. And when you add them together, you have 3. So the 3 isotopes of hydrogen are, don't forget, protium, deuterium, and tritium. The first one has an atomic number of 1 and a mass number of 1. You can see it over here. And then the second one has a mass number of 2. Look at the mass number of 2 written over here. And the atomic number remained the same, 1. The third one also has an atomic number of 1, but a mass number of 3. So you can see all of them are isotopes because they all have the same atomic number, but different mass numbers. Are we all clear on that?
Yes, sir.
Good. So we went all through this so that we'll be able to build a proper foundation for the next thing that we want to go into, which is electronic configuration. Now, before we proceed, let me throw the question open to the class. When that phrase electronic configuration is mentioned, what comes to your mind? Yes, I want 1 or 2 people to attempt that. When the word or when the phrase electronic configuration is mentioned, what comes to your mind? Yes, nobody wants to try. Should I mention names? David, Nifemi,
Electron,
Francis.
where the electron is positioned on the atom.
Okay, I can accept that. I can accept that as an elementary definition. Who else wants to try?
Where the electrons are present on the shells.
Okay, I can also accept that as an elementary definition. One more person and then we'll proceed. Anybody else? Anybody else? All right, in the absence of any other trial, let's proceed. I'm going to be breaking this down step by step, okay? So I just want you to relax and enjoy every bit of what I have for you. We're going to be building from the ground up, slowly and clearly. First things first, the electronic configuration is just the address of each electron in an atom where it lives. For instance, now, if you meet me and you say, Uncle David, where do you live or where is your address? Then I'll begin to tell you something like, okay, if you come to Nigeria, that is the country where I stay. Then you come to a city or a state called Sokoto. That is the city where I live in. Then if you come to Sokoto, you move to somewhere that is called Tamaji. And then when you come to Tamaji, you come to Golden Heritage Academy. When you come there, you are going to see me. You can see how I broke down my address in such a way that anybody who sees this will be able to find me. In the same way, an electronic configuration works like that. An electronic configuration is simply just the address of each electron in an atom where it lives. So for instance now, let's say sodium, Na. In our previous example, we saw that sodium has 11 electrons. When we write out the electronic configuration for sodium, we are simply showing where each of those electrons are positioned. We are showing that, okay, this electron, this is where it is. That electron, this is where it is. The other one, this is where it is, from number 1 to number 11. Is anybody confused, please? Do you understand what I just said?
Yes.
All right, very good. I'm so excited that we're all following. All right, good. I'm so excited that we're all following. So now, remember this. We have said earlier on that a nucleus is the center of an atom. That is where we have the protons and the neutrons. And we also said that the electrons are moving around the nucleus. Now, look at this structure of the atom over here. You can see that the electrons are scattered all across. All of them are not located in one place. So the electronic configuration simply tells us where each and every single one electron is located. So now let's get into the nitty-gritty of today's class, the electronic configuration. What can you see on the screen? I want someone to please speak up for me. What can you see on the screen right now?
Houses.
Okay, good. How about the write-up on the screen? Can you see some write-ups there?
Yes, sir.
Okay, good. What is the write-up that you can see? Can you read it out for me?
You see an atom just like an estate.
Very good.
You have multiple houses.
Mm-hmm. Go ahead, go ahead.
You have multiple houses. You have multiple houses inside with numbers 1, 2, 3, 4. Let's call them energy levels, aka shells.
Good. So let me explain. You see, an atom is just like an estate. You all know what an estate is, right?
Yes,
Yes,
sir.
sir.
Good. What's an estate?
An estate is
a
a
place
large compound where
so many
different houses are.
Thank you very much. A large compound that has plenty houses inside.
Plenty residential buildings.
Thank you. Plenty residential buildings inside. An atom is just like that. Inside estate, you have plenty houses. Inside an atom, you have plenty shells. So those shells now are just like the houses that you find in an estate. So if the shells are like the houses, then the people that live inside are called the electrons. Did you see that? Inside an estate, you have plenty houses, and then those houses have people that live inside. An atom is just like that estate. An atom has plenty shells contained inside it. Some atoms have more shells than other ones, okay? But depending on the number of shells that are present there, we have electrons that are staying inside each and every one of those shells. Can we proceed? Did you understand the analogy that I just gave?
Yes.
Are you sure?
Yes, sir.
All right, very good. So now, look at this, my analogy. I want it to be as simple as possible. An atom is just like an estate. The shells inside an atom are like the houses in the estate. Every estate has plenty houses inside. In the same way, atoms have different shells inside them. Now, inside an estate where you have houses, there are people that are staying in those houses, correct? I know I am correct. Now, in the atom, the shells that are present in the atom also have electrons that are living inside them. So electronic configuration is simply a way of showing us where each electron is located in each shell of the atom. Did you get that?
Yes, sir.
Is anybody confused about anything? Any questions?
No, sir.
All right,
No,
now.
sir.
So we're going to be learning how to write the electronic configuration for atoms. So first things first, it is important to also know that just like the houses in an estate, each house has a maximum number of people that it can accommodate. For instance, let's say you go to any estate and then you say, okay, I want to rent this house. The landlord will tell you, okay, when you rent this house, only 8 people are permitted to live inside this house. In other words, they are telling you the maximum number of people that can stay inside. If you bring 2 people, the house can contain them. If you bring 3 people, it can contain them. If you bring 7 people, it can contain them. But anything that is more than 8, you will not be allowed to bring them because it is more than the capacity of that house. In the same way, in every atom, there are shells that are surrounding the atom. You can see my drawing on the screen, right? Can you see
Yes,
my
sir.
drawing? Very good. Now, each of these shells are numbered 1, 2, 3, and so on and so forth. Each of these shell has a maximum number of electrons that it can accommodate. Now, how do we know the maximum number of electrons it can accommodate? There is a formula. That formula is given by 2 multiplied by n raised to power of 2. Now, let me show you how to do it. This n here simply represents the number of the shell. So, for example, now, let's say you have shell number 1. What is the maximum number of electrons that can stay there? I will simply say 2 multiplied by n raised to power of 2. Since it is shell number 1, my n here will now be number 1. Therefore, it will now be 2 times 1 raised to power 2. Now, I want someone to give me the answer to this. 2 times 1 raised to power of 2 is what?
2.
Very
Two.
good. Very good. Very good. Very good. 2 times 1 raised to the power of 2 is 2. In other words, the maximum number of electrons that can stay in shell number 1, which is this one over here, is 2. Did you see that?
No.
Yeah.
Is anybody
Yes,
confused?
sir.
Sir.
Very good.
No, sir.
All right, good.
No.
So now, if it is shell number 2, what is the maximum number of electrons that can stay there? I will simply come and use my formula, 2 times n raised to power of 2. Now, since it is shell number 2, my n will now become 2 now. So I have 2 times 2 raised to power of 2. Somebody give me the answer to this.
4.
Are you
8.
sure?
8.
Are you sure? 8.
8.
2 raised to power of 2
8.
is 4, and 4 times 2 gives me 8. Did you see that?
Yes.
Very good. So now I want somebody to calculate for me what is the maximum number of electrons that can stay in shell number 3. Go ahead and calculate that for me.
18.
18.
2 times n raised to power of 2. So we have 3 raised to power of 2. 2 times this gives us 18. Very, very good. I'm super excited that you are following. Now, this is showing us the maximum number of electrons that can stay in each shell. So when you have an atom and it has one shell, shell number 1 can accommodate 2 electrons, a maximum of 2. Shell number 2 can accommodate a maximum of 8 electrons. If you bring anything less than 8, it can accommodate it, but anything more than 8 will not be able to stay. Hello, are you there? Did you get what I just explained? Very
Yes,
good.
sir.
Yes.
So now that we know how to calculate the number of electrons that can stay in each shell, remember I told you, remember my analogy, that an atom is just like an estate, right? And then that estate contains multiple houses. The shells inside the atom, they are like the houses in that estate. Now, when you pack to a new house, is everybody going to stay inside one room?
No, sir.
No, Everybody
Yes,
are
sir.
going to go to different rooms. They are going to
Yes, sir.
arrange it. For instance, mommy and daddy will say, okay, we're going to stay in the master bedroom. Your elder brother might say, I'm going to stay in the visitor's room. You will say, okay, I have my own room. Everybody are going to arrange themselves in different rooms. In the same ways, when electrons are arranged in an atom, they don't stay in the same shell. Now, those shells are like the rooms in your houses. So basically, we have 4 different types of shells or subshells in atomic configuration. What are they? They are called the S, P, D, and F shells. Somebody say SPDF.
SPDF.
PDF.
Thank you very much. Thank you very much. I'm so glad that you are following. So these are the various types of subshells that we have in an atom. These subshells are the ones that contain the electrons in an atom. Are you there?
Yes, sir.
So how many
Yes,
types
sir.
of subshells do we have?
4.
Well,
Okay, what are they?
SPDF.
Good.
PDF.
Very good.
SPDF.
Very good. I hope you're taking notes.
SPDF.
Very good. I hope you're taking
Yes, sir.
notes. Very good. So
Yes,
now,
sir.
the first shell, which is the S shell, is a simple shell that can host 2 electrons. The second one, which is the P shell, is one that can host a maximum of 6 electrons. And then the third one, which is the D shell, it can host a maximum of 10 electrons. And then the final one, which is the F subshell, it can host a maximum of 14 electrons. If you're writing it down, can you please write this down for me?
Okay, sir.
Is anybody writing?
Yes, sir.
Yes, sir.
All right, so we have 4 basic types of subshells in atomic configuration. They are the SPDF. The S subshells can contain 2 electrons. The P subshell can contain 6 electrons. The D subshells can contain 10 electrons, and then the F can contain 14 electrons. Write that down. When you are done, tell me that you're done, and then we will proceed to the next thing that we have.
Done.
Are you
So I have
done?
a question.
Oh, please ask your question. I'm here to help.
So my question is that why are they called like, is there a particular reason for those letters to be chosen, or
Okay.
they just like to choose those particular letters?
Okay. I don't want to go ahead of myself. That is actually one of the things that we'll be treating in the next class. This is just the foundation that I want us to pay attention to, okay? I'll be treating that question in the next class where we'll deal with something that relates to this. So make sure that you keep this your question, okay? In our next
Yes,
class,
sir.
remind me and then we'll bring it and relate it to something that we want to do. Does anybody else have another question?
No, sir.
No, sir.
Okay, so we have seen the 4 types of subshells that we have. So now let's see some questions that I want you to answer. Quick mental check, no pressure. I want to see if you've been following this class thus far. Now, the shells in an atom are like the dash in an estate. Who wants to answer that question?
Me, sir.
How?
Yes, the shells in an atom are like the houses in an estate. Now, shells with lower numbers have dash energy than shells with higher numbers. Who wants to answer that question?
Lower energy.
Thank you. Lower energy. You know, when we were calculating number of shells and the number of electrons that it can occupy, we said if it is shell number 1, it can take 2 electrons. Do you remember? And then we
Yes,
said
sir.
if it is shell number 2, it can take a maximum of 8 electrons. The higher the number of electrons that a shell can take, the higher the energy level of that shell. So shells with lower numbers have lower energy than shells with higher numbers. Thank you for that answer. I'm super excited. And then thirdly, the third shell n is equal to 3, how many electrons can it accommodate? Who wants to answer that question for me?
18.
18.
Thank you very much. 18. And what was the formula that we used?
2
2
times
times n raised to power 2.
Thank you very much. 2 times n raised to power 2. And what does this n stand for?
number
Number
of
of
shells.
shells.
Thank you very much. It stands for the number of the shell that we are dealing with. Let me clap for all of you because you've made this class absolutely interesting for me. Even me, I'm learning from each and every one of you. So now let's talk about electronic configuration properly. We already said, who can read for me what's on the screen right now? I want somebody to read for me.
The room slash sub
We
shells.
already said
Yes, go ahead.
SPDF.
Mm-hmm.
We already said shells
Said
are like
Shells are like houses
In an
in an
estate.
estate,
Mm-hmm.
but
but each houses has different
has
rooms,
different
subshells.
Mm-hmm.
shells.
These
these
subshells are
subshells
labeled
are labeled
SPDF.
Mm-hmm.
Now
Now,
remember
remember
those
those
rooms,
rooms
subshells
or
Subshells
subshells
are
are
meant
meant
to
to
accommodate
accommodate
people,
Now let me
electrons.
explain. Thank you. Let me explain what we mean. Remember, we said that the shells are like the houses in an estate. Now, what is so special about a house? A house has different rooms. So if a shell is like the house in an estate, it means that every shell has different subshells that are under it. Now, those subshells are like the rooms in your house. And then we have 4 different types of subshells, and we mentioned that they are the S, P, D, and F subshells. So these subshells are the places where electrons are accommodated or reside. So let's see how to write down electronic configuration. We are bringing everything together now. How are these rooms arranged in each house? Here is the sequence, and I want you to pay attention. Are you with me on this?
Yes, sir.
Very
Yes,
good.
sir.
Good, good. So now let's pay attention. When it is the first shell, remember I said that the shell is like the house. Do you remember that?
Yes, sir.
Very good. So when it is the first shell, shell number 1, let me write it. Shell number 1. The number of subshells that are inside is just 1, S. And the first subshell is called the S subshell. Number 1, and then S subshell. And remember, how many electrons did I tell you that the S subshell can accommodate?
2.
2.
Thank you very much. 2 electrons. When you come to this, yes, when you come to shell number 2, let me put the number 2. When you come to shell number 2, the number of subshells that you have are 2. We have the S and then we have the P subshells. Do you see how I outlined them?
Yes, sir.
Yes,
Are you
sir.
sure you saw how I outlined them?
Yes, sir.
Yes.
Very good. How many electrons did I tell you that the P subshell can accommodate?
6 electrons.
Thank you very much. The P subshell can accommodate 6 electrons. And then at the third shell, we have 3. The number of subshells we have are S, P, D. Let me put the number 3S, 3P, and 3D. How many electrons did I tell you that the D subshell can accommodate?
10
18.
electrons.
How many?
10.
10
18.
electrons.
I'm hearing some people saying 8, some people are saying 10. Which one are we following?
10.
10 electrons. The D subshell can accommodate 10 electrons. And then when we come to the 4th level, we have 4S, 4P, 4D, and 4F. How many electrons did I say the F subshell can accommodate?
14.
14.
Thank you very much. Now, look at this drawing that I have on the screen right here. Did you see what I just labeled?
Yes, sir.
Can you all see what I just
Yes, sir.
labeled?
Yes, sir.
Good. What I just labeled now is the arrangement that electrons actually follow to occupy the subshells in an atom. Now, how do we follow this sequence? Can you see these red arrows that I'm labeling? These red arrows?
Yes,
Yes,
sir.
sir.
Good. We are going to be following them in order to get the sequence. Can we do that?
Yes,
Yes, sir.
All
sir.
right. So for arrow number 1, what does it touch? It touches 1s, right?
Yes,
Yes,
sir.
sir.
For arrow number 2, what does it touch?
2S.
Thank
Two
you.
S.
Arrow number 3, what does it touch?
2P
2P,
and
3S.
And
So
3S.
thank you. I'm writing 2p and 3s. For arrow number 4, what does it touch?
3P
3P,
and
4S.
3p, 4s. Thank you. For arrow number 5, what does it touch?
3D,
3D,
Mhm.
4P,
4P,
and 5S.
5S.
Thank you. 5s. And then for arrow number 6, what does it touch?
4D,
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 5D, and 6S.
5p, and 6x. How about for arrow number 7? What does it touch?
4F,
Yes.
5D,
Mm-hmm.
6D,
Uh-huh.
and 7.
7s.
7S.
Thank you. And then for arrow number 8, the last one, what does it touch?
5F,
5f, 6d,
6D,
and
and
7p.
7P.
Now, this sequence that we just followed shows us the sequence or the arrangement that we must follow when we are writing electronic configuration. And I'm going to show you how we are going to apply that. Are you ready to see it now?
Yes, sir.
Are you sure? Are you ready to see it now?
Yes.
Good.
sir.
So here is one example. The example on the screen says, write the electronic configuration of oxygen. Write the electronic configuration of oxygen. So now, when you have a question like this, the first question you should ask yourself is, how many electrons are present in oxygen?
8.
How did you know it's 8 is 8? Yes, do you want to tell me why? How did you know it is 8? 8 is correct, oh, but I just want to know if you know why it is 8.
It's number 8 in the periodic table.
Thank you very much. It is number 8 on the periodic table. In other words, it's atomic number. Remember, we defined atomic number earlier on in today's class, right?
Yes, sir.
Yes. And what did we
Yes.
say? What did we say atomic number is?
Number in periodic table?
The
Yes.
number of protons in an atom.
Thank you very much. The number of protons that are present in an atom. Also, an atomic number is simply the number of electrons in a neutral atom. So when you are asked to write the electronic configuration, step number 1, know the atomic number. When we say know the atomic number, what we mean is know the number of electrons present. Are you there?
Yes, sir.
Can somebody write down what I just wrote on the screen? Step 1, know the atomic number, which means know the number of electrons that are present. Can you write that for me?
Yes, sir.
Yes, sir.
If you've written that down, let me know.
Done.
Good, very good. So now, step number 2 is to write down the electronic configuration. How are we going to do it? We are going to follow this sequence over here. So now, watch what I'm going to do. The first arrow touches 1s. Is that correct?
Yes,
Yes.
sir.
And then we have 8 electrons. In other words, we want to show how these electrons are going to be arranged. Are you there with me?
Yes, sir.
Good.
Yes,
Yeah.
Remember, we talked about the s, p, d, f subshells. How many electrons can stay inside the s subshell?
Two.
two.
Good. So
2.
that means for this one s, 2 electrons are staying there. So we are going to write the 2 above the s like this. In other words, we are telling them that in the s subshell, there are 2 electrons that are staying there. Now we have provided accommodation for 2 electrons. How many is remaining for us to provide accommodation for?
6.
6.
Thank you. We are providing for 6 more. So the next arrow, you can see it over here. What does it touch?
2s.
Thank you.
2s.
It touches 2s. How many electrons can stay in the s subshell?
2.
2.
2. We put the 2 above. Are you understanding what I'm doing?
Yes, sir.
Are you
Yes, sir.
confused?
No.
Are you
Yes.
sure?
Yes.
Don't worry, we're going to do another example, okay? So we've seen the second one, 2s. 2 electrons are staying there. Now, how many electrons have we provided accommodation for thus far?
4.
Thank you. We've
4.
provided for 4. 2 over here and 2 over here. So how many is remaining now?
4.
4.
Thank you. So we want to provide accommodation for the remaining 4. So to do that, we'll come back to this our arrangements here. Look at this arrow. What does the arrow touch?
2.
2.
4.
Thank you.
3.
The arrow touches 2p. Now, before we write down, yes, the arrow touches 2p and it touches 3s. Now, the p subshell over here, how many electrons can it accommodate?
6.
It can accommodate 6 electrons. But how many do we have remaining?
4.
4.
So we'll
4.
just simply, is 4 less than 6 or greater than 6?
Less than
Less than 6.
So that means 4 can comfortably stay here. We will put our 4 here. And then this one that is here, we don't need it. We'll just clean everything out. So this is the electronic configuration for oxygen. 1s2, 2s2, and 2p4. Do you know what this means?
No, sir.
I'm going to
No,
explain.
sir.
I'm going to explain what it means. These numbers that you are seeing here, the 1 and the 2, they stand for the number of the shell. Did you see that?
Yes, sir.
Good.
Yes.
And then this number that are above, these ones that are up, 2, 2, and 4, they stand for the number of electrons that are present. So now, from this information, I can draw the electronic configuration of oxygen. So this one here tells me that it is shell number 1. So let me write the name of oxygen. This is oxygen. And then let me draw the first shell, shell number 1. Did you see that?
Yes,
Yes,
sir.
sir.
How many electrons are here?
2.
2.
So I'm going to
2.
draw the 2 electrons. 1, 2. And then I will come to the second one. What is the number of the shell here?
Shell 2.
Thank you. So I'm going to
Shell 2.
draw the second shell, which is shell number 2. Now, how many electrons are located at first here?
2.
Thank you.
2.
So I'm
2
going,
shell.
thank you. I'm going to draw them 1, 2. And then finally, I've come to the third one. What is the number here?
2.
Thank you. So that is still shell number 2. I'm not going to draw a new shell because it is still shell number 2. Do you understand?
Yes,
Yes,
sir.
sir.
How many electrons are remaining to be drawn?
4.
4.
Thank you. So I'm going to draw my 4 electrons. 1, 2, 3, 4. So you can see from the electronic configuration 1s2, 2s2, 2p4, I was able to draw what the atom of oxygen would look like. I'm going to do another example, okay? Because I don't want you to be confused. Can we do another example?
Yes, sir.
Yes.
Yes, sir.
Is the class boring?
No, sir.
No.
Okay. So now, That is what chemists mean when they write all those little 1s2, 2s2 things. They are simply showing us the address of the electrons in an atom. Let's do another example. Let's write the atomic number or the atomic configuration of carbon. So what did I say is step number 1?
Know the number
Know
of
the atomic number of electrons.
Thank you. Know the atomic number or the number of electrons. Now, for carbon, how many electrons do I have?
6.
Thank you. You can see it written over here. 6. I have 6 electrons. In other words, we want to provide accommodation for 6 electrons. Did you see that?
Yes, sir.
All right, so how am I going to start? Remember, I am using this, my arrangement over here. Are you seeing it?
Yes, sir.
Good. So what is the first one? I'm going to start from the first arrow. And what does the first arrow touch?
1s.
The first arrow touches 1s. And remember, we are using the SPDF subshells. So for 1s now, for the S subshell, how many electrons can stay there?
2.
Thank you. So I put my 2 on top. I've taken care of 2 electrons. How many is remaining now?
4.
Thank you. Because I have a total of 6. And if I've provided accommodation for 2, it means I have 4 remaining. So the next one, I'm going to come to the second arrow. What does the second arrow touch?
2s.
Thank you. I'm going to write that. Now, is this still the S or another letter? It is still S, right?
Yes, sir.
So how many electrons can stay in the S subshell?
2.
Thank you. So I've put my 2. So thus far now, I have provided accommodation for 4 electrons. Is that correct?
Yes, sir.
How many is remaining?
2.
Remaining 2 because I have a total of 6. So what does the next arrow touch? I want somebody to tell me.
2p.
Thank you. The next arrow touches 2p. Now, how many electrons can stay in the p subshell?
6.
Thank you. 6. But how many do I have left?
2.
I have 2 electrons left. So what am I going to put? I'm going to put 2 because 2 is less than 6, which is the capacity of the p subshell. So this is the electronic configuration of carbon. Can somebody read it for me? 1s2, 2s2, and 2p2. Did you see that?
Yes, sir.
Now, from this information, 1s2, 2s2, and 2p2, I can draw what the atomic structure will look like. Can we do that?
Yes, sir.
Yes.
So the first thing I will do is to look at the numbers. So I have the first number here, which is shell number 1. So let me write the name carbon. Let me draw the shell number 1, the first shell. So now from the first shell, you can see it has an S subshell. How many electrons are there?
2.
So I'm going to draw the electrons, 1, 2. And then the next one, what is the next number?
2.
So that is telling me that I'm going to draw shell number 2.
2.
Did you see that?
Yes, sir.
Good. How many electrons are here?
2.
So I'm going to draw them 1, 2. So the next one, what is the shell number?
2.
Am I going to draw a new shell?
No.
Because it is shell number 2 and I've already drawn it. How many electrons are still here?
2.
So I'm going to put it 1, 2. So now let's count. What is the total number of electrons that I have? 1, 2, 3, 4, 5.
6.
What is the total number of electrons that I have?
6.
Is it the same with the atomic number here, which is 6?
Yes.
Yes.
So you can see that I am very correct. Is that correct?
Yes, sir. Yes,
So
sir.
now I want you people to help me. This is the next element that we have, calcium. Calcium has the atomic number of 20. In other words, we have 20 electrons. Can you help me write the electronic configuration of calcium?
Yes, sir.
Are you sure? Do you want to try?
Yes, sir. Yes, sir.
Yes, sir.
Yeah, I know I have a bunch of geniuses here. Oh yeah, let's do that. Should we do it together?
Yes, sir.
All right, so you tell me now, you're the one in charge, you're the teacher now, I'm the student. Oh, what is the first thing that I will do?
Know your number
We'll
of
look at our
electrons.
electronic configuration.
Okay, what is the step number one? What am I going to do first?
Know the
Know
atomic
the atomic
number.
number.
Okay, I will know the atomic number, the number of electrons. Okay, so I've done that now. We have 20 electrons. What is step number 2?
We'll look at our electronic configuration.
Thank you. I'm going to look at the electronic configuration, this pattern over here, and I'm going to follow it.
Yes.
So now let's start. What is the first thing I will do?
The first arrow you see, you write 1S.
Okay, the first arrow is 1s. How many electrons can stay here?
2.
I've written 2. How many electrons are remaining now?
18.
Good. So what is the next thing to write? What does the next arrow touch?
2S.
Okay, let me write it. 2s. How many electrons can stay here?
2.
2.
Okay, let me write it. How many electrons are remaining for me to provide accommodation for?
16.
Thank you. 16. Let's go. What is the next thing I'll write?
2p.
Okay, 2p. How many electrons can stay here?
6.
6.
Good. How many have I provided accommodation for thus far?
10.
So how many is remaining?
8.
10.
10. Thank you. Because we have a total of 20 and I've provided an accommodation for 10. 2 here, 2 here, and 6 here. So what is the next thing I'll write?
3s.
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 Good. How many electrons can stay here?
2.
Okay, I've put my 2. How many electrons are remaining for me to take care of?
8.
8.
Thank you very much. So what's the next thing I'm going to write now?
3p.
3p.
Thank you. 3p. How many electrons can stay in this one?
6.
6.
I've put my 2. So let's count. How many do we have? We have 2 here. 2 plus 2. That's 4.
4.
4.
4 plus 6.
10.
10.
10 plus 2.
10.
12.
12 plus 6.
18.
18.
12 plus 6 gives us 18. How many is remaining now?
2.
2.
Good. So what is the next thing I'm going to write?
4s.
4S.
4s. How many electrons can stay here?
4S. 2.
Thank you very much. 2. So altogether, this gives me the electronic configuration of calcium. Did you understand it?
Yes, sir.
Yes, sir.
Was it confusing?
No, sir.
Are you
Yes, sir.
sure?
Yes, sir.
Yes.
Now,
sir.
from this information, I can still draw what the atomic structure would look like. Can we do that?
Yes, sir.
Yes,
All right.
sir.
So let me write the name, calcium, Ca.
Calcium.
So we have the first number. The number tells us the number of the shell. This is shell number 1. Is that correct?
Yes, sir.
Yes, sir.
I've drawn it. Oh, shell number 1. How many electrons are here?
2.
So let me
2.
draw it. 1, 2 electrons. So we have the second one, which is shell number 2. So am I going to draw the second shell?
Yes, sir.
Yes. I've drawn it now. How many electrons are here?
2.
Thank you. I've drawn it 1 and 2. And then I have the next one. What is the shell number here?
2.
Good. So am I going to draw another shell?
No.
Good,
No.
because it's shell number 2. How many electrons are here?
6.
So let me
6.
draw them 6. 1, 2, 3, 4, 5, and 6. Did you see how I did that?
Yes, sir.
Yes,
What is the
sir.
next one?
3.
Shell number 3. So let's draw it now. We have drawn the third shell. How many electrons are here?
2.
2.
So let me put my 2. 1 and 2. So now, the next one is what?
3.
Thank you. So I'm still on the third shell, right?
Right.
Yes, sir.
So how many electrons are here?
6.
6.
So let me draw them. 1, 2, 3, 4, 5, and 6. Did you see how I drew it?
Yes,
Yes,
sir.
sir.
And then finally, I have 4s. Who can tell me what I'm going to do here now?
Draw shell number 4.
Draw the fourth.
Thank you. The number there tells me the number of the shell. So I'm going to draw shell number 4. So now, how many electrons are going to be there now?
2.
1 and 2. If you count everything together, I guarantee you are going to arrive at the number of 20. This is what the electronic configuration is all about. It shows us how electrons are arranged in the different shells of an atom. Did you understand everything we did throughout today?
Yes, sir.
Was it confusing?
Yes, sir.
Was it confusing?
No, sir.
Can you do
No,
some?
sir.
Can I give you some assignments?
Yes, sir.
Yes, sir.
All right, so with that, we have come to the end of today's lesson. Let me give you people a round of applause. Thank you for staying with me up until this point. So here are the assignments that I want to give to you. I want you to draw the electronic configuration of some elements. Can you do that for me?
Yes, sir.
As your
sir.
assignment, I'm going to drop the link in the community, so you will do that for me. So let me go to the assignment tab.
Mm. Mm.
Yes. So here are your assignments. Can you read what is on the screen?
Yes, sir.
Okay, go ahead.
Write the
Right.
electron.
The electron configuration of
Of the following. The first
Of the following.
Yeah, the first one is the letter V. V stands for the element that is called vanadium.
Vanadium.
Yes.
Vanadium.
The number of electrons that we have is what?
23.
Vanadium.
23.
23.
Good. The next element that we have is what?
Magnesium.
Magnesium.
Thank you. Mg stands for magnesium. How many electrons do we have?
12.
12.
Good. Are you writing down your assignment? I'm going to drop the link, okay?
Yes, sir.
And then the next one is N. N stands for what?
Nitrogen.
Thank you
Nitrogen.
very much. Thank you very much. You all are a bunch of geniuses. I'm so excited. How many electrons are here?
14.
And then finally we have K. K stands for what?
Potassium.
Thank you.
Potassium.
Thank you. Thank you. Potassium. Potassium. How many electrons are there?
19.
19.
19. So this is what I want you to do. I want you to draw for me the electronic configuration, and then when you do that, you draw the atomic structure. Can you do it for me?
Yes,
Yes,
sir.
sir.
I'm looking forward to seeing your responses, okay? With that,
Yes, sir.
we have come to the end of today's class. Thank you all for staying tuned with me. I remain. Do you remember my name?
Yes, sir.
Yes, sir.
What's my name?
Mr. David.
All right. Thank you very much for staying with me till the end of this class. I want to see your assignments, okay? Our next class is going to be on when? Do you know when our next class is going to be? Thank you very much. Our next class is going to be on Friday. We have classes 2 times in a week. So I will see your assignments when you do them, okay?
Okay, sir.
Okay,
Thank
sir.
you very much. Bye.
Bye.
Bye-bye.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.